All right, guys, central limit theorem for proportions. If you go to Blackboard under handouts, you can find this handout if you want to print it out. I think it works best that way. Let me get down a little bit closer to this so you can maybe read it better. I don't know. Let me improve the quality. All right. First problem says, according to a recent poll, 10% of the population is left-handed. Find the approximate probability that a random sample of 1,000 people will contain 11% or more left-handed people. So guys, the 10% describes the population. So we know that P is going to be equal to 0.10. And from the previous videos, that tells us that the mean of the sampling distribution of the sample proportion will be equal to P. And the standard deviation of the distribution of sample proportions will be equal to P times 1 minus P over N, which is the square root of 0.10 times 0.90 over 1,000. So let's see what that is. So that's 0.0095. So we got to 4 places. Now, find the approximate probability the random sample of 1,000 will contain 11% or more. So the distribution that we have here has a mean of 10%. So it's centered at 0.10, but we want 0.11 or more. So guys, you should know by now that you go to Stack Crunch to do this. So let me get rid of previous stuff. Go to Calculator, go to Normal. So I have a mean of 0.1. I have a standard deviation, the square root of 0.1 times 0.9 divided by my sample size, which is 1,000. And I want, what, greater than 0.11. So guys, the correct answer would be 0.1459. Now, let me point something out. I have the mean of 0.1 because 10% of the population that we're examining, which is being left-handed, is 10%. I can go over here and get rid of all that. If I just want to come in and put 0.0095 that we got from taking the square root of 0.1 times 0.9, I can do that. And you'll see that my answer is off a little bit. The correct answer is 0.1459. This would be 0.1463. If you're going to do that, something that I would recommend is, let me go back over and demonstrate this to you. I would recommend going out to about 6 or 7 places. So if I go out 0.009487, what did I say? A 9487, is that right? Yeah. Or even going further, 868. If I go out further, I'm going to get an answer that becomes closer and closer. And if I do something goofy and just decide I'm going to go to 0.09, only 3 places, then I'm going to miss the mark by quite a bit. In fact, I missed it so much I probably missed the problem. So if you're going to take this approach, you need to go out probably 6 or 7 decimals on your standard error, standard deviation as it's called here, to get the correct answer. The easiest way to do it is just square root 0.10 times 0.90 divided by your sample size, which is 1,000. Close it up, And guys, you got no problems there. You don't have to worry about how far it rounds out. You're going to get the theoretical answer that way, not an estimated answer. All right. So as you've seen, I've already put the correct answer in 0.1459. Number 2, according to a recent poll, 10% are left-handed. Same setup, but the difference here, find the approximate probability that a random sample of 1,000 people will contain 120 or less. So guys, now you're not given a percentage like you were up here. You got to work a little bit to get your p-hat. So it's 120 out of the 1,000. Guys, I know what this is, but some of you may not. Some of you may not be. That's too many. Geek like me. So it's 0.12. So guys, this is the same problem we have up here, except I want the probability 0.12. And I want less instead of more. So easy to do in Stack Crunch. I've got my mean. My standard deviation remains the same because I have the same sample size. Now, if the sample size had changed from 1,000 to something else, I'd have to modify this. Now I need less than 0.12. So guys, the computation gives us 0.9825. That's the correct answer. And I'm not really sure what my math lab will ask you to round to, but it seems to me on proportions they usually require you to round to 4 places. So that's why I'm illustrating the answers like this. All right, one more problem. If I can get it separated here. Okay, okay, a multiple choice test. So I haven't done this problem. So choices A, B, C, or D. So we have a 1/4 probability of getting each question correct. It has 30 questions. A passing grade is 70% or higher. A student has failed to study or attend class. That's promising. And is therefore required to guess on each question. I actually have a story I could insert here, but I won't. Okay, what is the probability that a student will guess correctly on one question? Well, you have 4 options. There are 4 answers, and one of them is correct. So we know now that we can express that as a fraction or a decimal or a percent. Since the one probability, we would report probably that one. What is the probability that a student will guess? Actually, guys, that's not what I intended to ask. I intended to ask incorrectly. Well, guys, there's 3 ways to get it incorrectly out of 4 possibilities. But you guys wished it would stay this easy, right? All right, C, find the approximate probability that a student who is just guessing will pass the test. Well, this doesn't look good, does it? So the P is going to be, the probability is going to be 1/4. So this is going to be our mean. And our standard error is going to be the square root of P times 1 minus P over N, which in this case is 30. Now we are we're violating conditions here. I'll just go ahead and tell you. So really our answer to this, I'm going to go through it just to show you the steps, but our answer wouldn't be any good because if we look at N times P, N is 30, P is 0.25. That's 7.5, which is not greater than 10. So, guys, the answer that we get isn't going to, it's going to be an estimate, but it's going to be a wishy-washy estimate because we're violating a condition I talked about in a previous video. So remember, N times P and N times 1 minus P both have to be greater than or equal to 10, but I'm going to go ahead and work the problem anyway. So find the approximate probability that a student who's just guessing will pass pass the test. Well, guys, if you've only got a 0.25 probability of getting each question, and you have a passing grade of 70 or higher, well, it's just not going to happen. So the mean here would be 0.25. The standard deviation here would be the square root. 0.25 times 0.75 divided by the sample size of 30. And to pass, you're going to have to get a 0.70 or higher. This is going to be funny. It's not looking good. It's so tempting to think that that's 6.27, but guys, remember, a probability has to be between 0 and 1. And what this is, it's giving you the answer in scientific notation. This e to the negative 9 says we have to move this decimal place 9 places to the left and put in 8 zeros. So essentially, the answer would be 0.8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, one more. What was it? 6.3, is that right? Yeah, 6.3. So guys, you've got to, it's just not going to happen. Well, I mean, what is that really? Tenths, hundredths, thousandths, 10,000, 100,000, millions, 10 million, 100 million, 10 billion. You got a 63 out of 10 billion chance. That, I mean, it's getting into, it's almost the odds of winning the lottery, right? So, not very good. Let's go on to the next question. If a similar test was given with true-false. Now, if we go to true-false, then our probability of getting a correct question correct is 0.50, and then of course the probability of not getting it correct is also 0.50. Again, we're randomly guessing, so will it be higher or lower than the approximate probability of passing the multiple choice? Well, guys, clearly it's going to be higher, and you can see you're going to have a little bit more reasonable chance of passing. So I can put 0.50 there, and 0.50 there, still 30, and we need to go 0.70. So, I mean, you got kind of a chance, about 0.014. So it does go up. I mean, you've got like a 1/10, or 1/100th. Well, 14 thousandths probability. So it's not too good. But anyway, it does go up. So, guys, that's all I got. Take care.